Hey Team Bio, welcome to your screencast on kind of introduction to photosynthesis. This is actually, there are two reactions in photosynthesis, the light dependent reactions and the light independent reactions. And this is a screencast about the light-dependent reactions, which are happening within the thylakoid membrane system. So we're going to be discussing photosystems, pigments in those photosystems, and electron transport systems. Again, this is the light-dependent reactions. It's happening in the TMS, and it's kind of part one of photosynthesis. So this would be part one here, and this is part two here, which is going to be your next screencast. Okay, the overall chemical reaction for photosynthesis is CO2 plus H2O plus C6H12O6, which is glucose, and this is an arrow, not a plus. Plus oxygen, and then you also need energy to get this reaction going. Oops. Energy. So today we're going to be looking at what reactants and products we see being created or used up in this set of reactions, because not all of these components are used or created here today. Okay, and again, this is an unbalanced chemical equation. You can balance it if you want. It is not that hard to do. Okay, so we have looked at the structure of a leaf. In fact, in class today, you will be looking at this leaf cross-section and labeling the different pieces. And you all know that if you zoom in on one tiny little chloroplast, the structure of the chloroplast looks like this. It's a triple lipid bilayer. The outer membrane, the inner membrane, and the thylakoid membrane system are all lipid bilayers. And we're creating this internal environment inside the chloroplast where we can have differences across cell membranes. And we're going to zoom in on one tiny little piece of a chloroplast, one thylakoid, for the majority of this screencast. So just to get you oriented here in this little zoom in box, we have, this is the thylakoid membrane system inside of this piece, which is the thylakoid. So this is like one of the little jelly beans. We have, I guess I could say this whole thing is the TMS, the thylakoid membrane system. The lumen is the interior of the thylakoid. I'll just move that up a little bit. And then outside the thylakoid, in this area here, is the stroma, not to be confused with stomata. And this is like the jelly-like liquid that is outside of all the thylakoids, but inside the inner membrane. Okay, so that's where we are. It's like this little, we've just zoomed in on this little bit of the thylakoid membrane system right here. Okay, so what are we talking about? We're talking about the light-independent reactions. And the light-independent reactions all start in a structure that is called, kind of annoyingly, photosystem 2. It's called photosystem 2 because even though it's the first photosystem in a series of two photosystems, it was the one that was discovered second. We begin with photosystem 2. I apologize for that. Okay, what is a photosystem? A photosystem is a structured arrangement of a molecule that you already are all pretty well aware of. It is called chlorophyll. Chlorophyll is a little pigment. And it kind of looks like a lollipop. It has a ring structure at the top, and then it has a long tail. And as a pigment, it is really good at absorbing some types of light and reflecting other types of light. The type of light that it reflects is the color that it is. So chlorophyll is green because it is not absorbing green light. It is reflecting green light. Okay, so what does a photosystem actually do? It kind of functions like a satellite dish. It is going to collect a bunch of light and focus it all on one central pigment. So these are all chlorophyll molecules here, and then here is our central chlorophyll here, and these little wavy lines represent light. Okay, let's jump in to one chlorophyll organic compound right here, and look at the very center of it. At the center of this ring, it's called a perforin ring, there is an atom of magnesium. Magnesium is a type of metal, and it's good at, metals are very conductive because they're good at accepting and then giving away electrons. They don't hold on to their electrons very strongly. And there's also an interesting phenomenon with electrons where you have electrons that are in orbitals around the nucleus of an atom, right? And if a wave of light hits an electron, the electron is going to absorb that wave of light, and it's going to jump up to a higher energy state. The higher energy state that it jumps up to is exactly proportional to the energy of this wave of light. So if this light is at it has a certain amount of energy, then the electron, is going to jump up here. And now, the interesting thing about this is that not only does the electron jump up and reach this higher energy state, like a little further out from the nucleus, it can also re-emit that exact same wavelength of light, but in doing so, it falls back down to its original energy state. So this is a property of electrons. They can absorb light energy, they can jump up to a high energy state, they can also emit light energy and drop down to a lower energy state. So why is this all important? Because what's happening in a photosystem is that every individual chlorophyll molecule is absorbing light energy through the electrons that are in the central magnesium atom at the center of the ring. But then they re-emit that light energy, but they don't just re-emit it willy-nilly randomly like, ooh, way off here. They send it. They're able to channel the light energy that they're re-emitting down into the center of the photosystem. There are actually multiple chlorophylls in here, so this guy will pass it off to one right here, we'll pass it off to one right here, we'll pass it off to one right here, and eventually it's going to reach this center special, it's actually a pair of chlorophyll molecules here, but I've just drawn it as one. Okay, so it's acting like an antenna. Not only is this chlorophyll molecule receiving light and then channeling it towards the center, but this one is, and this one is, and this one is, and this one is, all of them. So what you get at the very center in this chlorophyll molecule is an electron that gets so excited that because it's absorbed so much light, so you can draw this like a ton of light is coming in and being focused on this electron. So there's so much light energy that's channeled towards this electron that not only is it able to jump up an orbital, but it's actually able to escape the orbit of the nucleus entirely. It is emitted as what's called an HEE, a high energy electron. Okay, so in this way, so this central chlorophyll molecule just got an electron just absorbed all this light energy that all these other chlorophyll molecules are channeling towards it, and now this electron is so excited it's able to escape the orbital of this central magnesium ion, and now it is a high energy electron. Okay, which brings us, so that's all happening here in photosystem 2. Okay. And I guess I should start out by saying that this electron that the magnesium atom is having came from a reaction called the photolysis of water. So at the very beginning of photosynthesis, water is split. So water comes in, it binds to this photosystem, and another function of this photosystem, in addition to kicking off a high energy electron, is to take water and split it up into its component pieces. It splits it up into 3 things. One is oxygen, molecular oxygen. So right away you're seeing one of the inputs to photosynthesis was water, and one of the outputs was O2. This is where the O2 is created, right at the very beginning. The other thing that gets split off from here is H plus ions, right? Because water is composed of hydrogen and oxygen. If you're splitting water up and you're making oxygen, you're also going to be kicking out some hydrogen ions. So hydrogen ions would be kicked out here. So for the splitting of this would actually be 2 waters, you make 1 oxygen, and you get 4 hydrogens. It's important where this is happening on the interior of the lumen, because the hydrogen concentration inside relative to outside the space is going to be important. So hydrogen ions are created in this process. And lastly, the whole point of this process is to take electrons, which are low energy when they come off of water. So we're stripping water of its electrons and we're dumping them on this central chlorophyll molecule here, and we're going to excite them using the light energy that we've gathered in the photosystem. So we split water. This whole reaction is called photolysis, or photolysis. Photo meaning light, lysis meaning to split. So we're splitting water with photons of light. And in doing so, we've created oxygen, we've created hydrogen, but most importantly, we've created some low energy electrons that we're going to excite using the photosystems. Okay, so all that is happening in photosystem 2. As soon as this central electron in the central chlorophyll molecule is a high energy electron, it's kicked out of the photosystem and it travels down what we call an electron transport system. So these 3 yellow dots represent an electron transport system. And they do exactly what you'd expect them to do. They transport electrons. So this is a high energy electron that is kicked out of the photosystem, and it's passed down to the first part of the electron transport system, or you'll also hear it called an electron transport chain because it's happening in a sequence. So this first part of the electron transport system, it takes the high energy electron and it uses a tiny little bit of the energy in the high energy electron to pump a hydrogen ion across the membrane. This is active transport because we're using the energy in the electron to move a hydrogen ion from an area of low hydrogen concentration, which is outside of the thylakoid, in the stroma, into the lumen of the thylakoid, which, as you know from before, we've already created some H plus in the photolysis of water. But we move another high energy, or another H plus ion in using the energy of the electron. Then, now the electron has a slightly lower energy. We pass it off, the electron off, to the next part of the chain. And the same thing happens. We use a little bit of the electron's energy to pump, this is active transport, a hydrogen ion into the lumen. And then the electron is now a little bit lower energy. And then we pass it off again. And the same thing happens. We use a little bit of that electron's energy and we pump a hydrogen ion into the lumen. So now, by the time that the electron has moved through this electron transport system and is passed off to our next photosystem, which annoyingly is called photosystem 1, this electron that arrives at photosystem 1 is a medium energy electron. It's not as low energy as when we stripped it off of this water molecule here before we excited it in the photosystem, but it's a lot lower than it was when we excited it using photons of light that were collected in this photosystem. But we used a bunch of that energy to pump hydrogen in. So arriving here, it's a medium energy electron. And now the exact same thing that happened in photosystem 2 is going to happen in photosystem 1 to this electron. We are going to aggregate light energy using this property of this central magnesium ion to absorb light with its electrons and then re-emit it, and it's channeled towards the central pair of chlorophyll molecules here, and then there's going to be so much light energy that's focused on this now medium energy electron that we're going to kick it off again as an even higher energy electron. And we are going to pass this light energy again down. This is an electron transport system again. Here's an ETS. And unlike the first electron transport system, the goal of this electron transport system is to pass off electrons to a high energy electron carrier molecule. So at the end of this pathway, we want electrons in a little safe electron suitcase that we can send to another part of the cell. So electrons are dangerous when they're high energy. They're reactive. They can perform reactions for you. And so if we don't package them in a way that's safe, they're going to do damage to this cell. So 2 electrons are aggregated at the end of this electron chain. They're very high energy. And we send in you can think of it like a lead suitcase that's going to carry radioactive material. It's high energy, which is why we need to keep it in this very protective suitcase. And that's going to allow us to transport this dangerous but powerful contents very, very safely. So our lead suitcase is called NADP+. And with a little bit, so this has a positive charge, we're going to add 2 negative charges. So we also need to add 1 H+ to our reaction, and we're going to pick up those 2 electrons. They're going to jump on to our suitcase, NADP+, and this whole compound is going to be called now NADPH. So this is just NADP+ with a hydrogen and then 2 electrons. So this is our high energy electron suitcase. It's going to safely carry our electrons to the next step. Not that this is super important, but the last part, this enzyme is called NADP+. I have written down reductase. I've written down reductape, but I think it's reductase. Yes, it would not be duct tape, it would be reductase. So it's actually reducing, NADP+. We'll talk about what oxidizing and reducing means more later. Okay, so we've created NADPH. This is very important because it is a product of the light independent reactions, and the light-dependent reactions, we're going to send it the goal of the light-dependent reactions is to gather the sun's energy and then store it in chemical energy. But this is kind of an unstable and unwieldy form of storing the energy, so we're going to store it in a ultimately in a much more convenient package, which is glucose. But here, this little molecule is storing light energy for us. Okay, but there's another piece to this as well. As you know, we've just pumped a bunch of hydrogen into the lumen of the thylakoid membrane system. And as you recall from your study of chemiosmosis, that there is potential energy in a concentration gradient across a semipermeable membrane. And would you know it, there is a bunch of ATP synthase molecules embedded in the thylakoid membrane. And because there is a concentration gradient of hydrogen across this membrane, there's a pressure out. Hydrogen is going to pass through the ATP synthase, and as it moves down its concentration gradient, it is going to drive the formation of ATP from ADP and phosphate. We're going to make ATP. So ATP is our second product of the light-dependent reactions. And we're going to send it to the light... Oh, should be independent. Sorry. We're going to send both NADPH, which is holding, remember, high energy electrons, and ATP, which is another chemical energy storage molecules. These will both go to the light independent reactions, and we will use them to make glucose. Okay, so this is it. This is one of the secrets of life. This is how light energy is in the first step of transformation to stable chemical energy that sustains almost all living things. Okay, sorry if it was a little long.